Hi, in this video, I'm going to go over the answers to Worksheet 3.1. So you can watch this video to either check your answers, or if you're stuck, you can use these to help you get unstuck. So let's take a look at this first one. And we're asked to try to find the position versus time graph. So we need to think about like, well, where does it start? So if this is 50 and this is 25, then that's probably 0, meaning that when t is equal to 0, meaning at the very beginning of the time, it starts at a position equal to 0. It's going to roll in the positive direction, so it's going to start to travel in the positive direction. And it starts out with an initial velocity of 0, meaning that it's going to start out flat, right? It's not going very fast. As time goes on, it's going to start getting faster and faster and faster, so that's going to make it look like a top opening parabola, like that. To do the velocity versus time graph, same kind of thought process. When time is equal to 0, our velocity is equal to 0. And so it's going to travel in the positive direction. So our velocity is going to get bigger and bigger and bigger in the positive direction. Lastly, a couple ways to think about your acceleration graph, right? Your acceleration comes from the slope of meaning the direction that the ramp is sloped. The ramp is sloped towards the positive side. It is, right, the acceleration is going to be caused by gravity, so that's going to give us a constant positive acceleration, pulling that object in the positive direction, that ball. For part D, it says write in an algebraic equation. So we're kind of meaning we need a relationship between time and position. And basically for all of these, for all part Ds, we're going to be referencing this kinematic equation right here, because that is a relationship between position and time. And so if we have an initial position, we'll fill that in. If we have an initial velocity, we'll leave that in. If there isn't initial position or initial velocity, we'll take that out. So in this case, our initial position is 0. So we would, right, if you put a 0 in there, that's going to take that term out. Our initial velocity is also 0, so that's going to take that middle term out, and you're only going to be left with the last one. So we would say that x is equal to 1/2 at squared. It's a generalized equation because we don't know what the acceleration is, so we just leave it like that. For part E, we're going to reference the first equation, kinematic equation, this one right here. Same deal. If we have an initial velocity, we'll go ahead and fill that in. If we don't, we'll leave it blank. Since in this case we don't have an initial velocity, it's 0, we'll leave that blank, and we'll just say that v is equal to at. So this graph would look, for any object going at any acceleration, given this scenario, that would be it. And I'm just going to leave part F off. I'm not going to talk about that one, or we're just not going to do that one. Let's take a look at the next one. So in this one, it says 0, 25. We can assume that we start at a position of 50. So that means it's going to start up here at a position of 50 meters. So, or centimeters, whatever it is. It says the initial velocity is 0. So that means that, again, it does start flat. It's going to be traveling in the negative direction because it's traveling towards 0 from positive 50. So it's going to start flat, and then it's going to be traveling towards 0, so that by the time it gets to 0, right, it's moving quite quickly, meaning our slope is pretty steep, and it's negative because we're traveling to the left in the negative direction. For our velocity versus time graph, we are again going to start at 0. So when the time is equal to 0, our position is equal to, or our velocity is equal to 0, because it tells us that. But this time, right, we're going to end up with a pretty big negative velocity. So that should be a linear line, but it would look like that. Our acceleration is, again, constant because it's being caused by gravity, and gravity isn't changing. But this time it's negative because it's pulling it, right? The ramp is sloped to the left, so it's pulling it in the negative direction. So now we go back and do the same reasoning that we did for part D, except that we're looking at this equation, and now we do have an initial position, right? We start at 50. This is still 0. And so And then we're still left with that part, though the acceleration is negative. So what that's going to do is we're going to be left with x is equal to 50 minus 1/2 at squared. Minus because the acceleration is negative in this case. So that's where the negative signs, you got to get a negative sign in there somewhere. This one is going to end up being that because, right, we go back to this kinematic equation. Again, our initial velocity is 0. Our acceleration is negative. So there you go. And again, I'm going to leave part F off. Moving along. In this one, it is, right, we are given an initial velocity, pushed up the ramp. We can assume that it starts from 0. So we start at 0, so that means that it's going to start right there. It's going to start by moving quickly in the positive direction, so that's going to be a steep positive line. And then it's going to flatten out as time goes on. And I'm just going to assume that the ball goes up to the top and stops. It doesn't say. It might go, you might have done it up and down, in which case your graph would look like that. And that is just as good. So it's fine. I guess I'm just going to assume that the problem is that it goes up to the top and then stops, like someone catches it. So it doesn't say that. It doesn't say either way. So I'll draw both of them for you. Either one's fine. So this would be just up, and this would be up and down. Your velocity versus time graph, right, starts with a positive velocity and ends with a 0 velocity, assuming that it just goes up. If you assume it goes up and down, it would look like that. And then lastly, your acceleration, right, your ramp is sloped to the left towards the negative sign. So either way, your line is going to look, your acceleration graph is going to look like that. So it doesn't really matter. So next up is to write the equation. In this case, we have no initial position. Right, again, we're starting from this kinematic equation. And so we don't have an initial position. We do have an initial velocity, and that our acceleration is negative again. So we're going to need to take that into account. So you're going to be x is equal to vt plus, nope, minus 1/2 at squared because of negative acceleration. The equation doesn't change. Sorry, x v naught. Our equation doesn't change if we let it go up or all the way, up and down or just up. So we just don't let t go as far. Same deal. Right, if we utilize this equation, we do have an initial velocity, we do have an acceleration. The acceleration is negative, so v is equal to v naught minus at. Again, we're not going to do that one. Okay, moving on to the next one. This one we just need to draw the graph. So again, it appears that we start at 0, so I know I'm going to start right there. We're going to have, or it's going to kind of change halfway through. So I'm going to put a little dotted line through each of these so that I can remind myself that it's going to, right, I'm going to do kind of half of one thing and half of the other. So it's going to start slowly. So that's going to mean it starts pretty flat. It's going to speed up as time goes on. So it's going to get steeper and steeper and steeper. And then once it gets to here, it's going to travel at a constant speed. So that's going to look like that. It is going to speed up for the first half of the time and then go at a constant speed for the second half of the time. And it will accelerate in the positive direction for the first part of the time and have no acceleration for the second half of the time. So just to go back, I think the trickiest part is this one because it's getting steeper and steeper and steeper because it's getting let's see here, because it's speeding up and then it's going to hold that speed, meaning it's going to hold that slope for the second part of the time. So that's why it changes from curved to linear, because it's speeding up in the first 25 centimeters and then it's going at a constant speed for the second 25 centimeters. So constant speed is a linear graph. So this one's kind of split into thirds. So we'll do that. So for the first third, it's just like the one above, so it's going to speed up. So kind of curved. Then it's going to hold that speed for the flat section. So then it's going to turn into a linear line. So curved linear line, and then it's going to flatten back out as it slows down. This one is going to, oh, it's shoot. Okay, ignore all of what I just said because it doesn't, right? It starts over here. Sorry, I didn't pay attention to that. So it starts over here. So that means it starts up here, starts slowly and speeds up, then goes at a constant speed, then flattens out. So it should look like that. Should be negative, then constant, then slows down to a stop. So that should look like that. And then it's accelerating in the negative direction at the beginning, not accelerating in the middle because it's flat, and then accelerating in the positive direction on the last one because this ramp is sloped towards the positive direction, right? So this negative acceleration, negative velocity is going to cause it to speed up. Zero acceleration is going to get it to go at a constant speed. And then positive acceleration, negative, it's going to go negative velocity, positive acceleration, that's going to cause it to slow down. So there we go. That one's kind of tricky, but hopefully that helps you understand it. So yeah, of course, if you have any questions, don't hesitate to contact me, but I hope this helps you. Thanks.